welcome to the third video segment for Module 5, which is the magnetic field inside of solenoid. In this video, I will explain in regards to the presentation PowerPoint that will be explained later on again by the lab assistants, and it is recommended for all participants of Basic Physics Laboratory to watch the first and second video for Module 5. So the outline for this video will be goals, equipment, basic theory, the standard operation procedure of experiment, data, analysis and discussion, and last but not least, the report format. So the goals for Module 5, magnetic field inside solenoid, there are four. The first one is to determine the relationship between current and magnetic field, followed by determine the relationship between the number of coils and magnetic field, and then to calculate the value of vacuum permeability constant or mu0 within the experiments, and last but not least is to calculate the magnetic field inside and outside of the solenoid. So there are a total of 7 tools and materials that will be used in this module. The first tool is LabQuiz interface to act as a computer for this experiment. Second one is the power supply DC variable 3A to provide power in the form of voltage to this experiment, and then ampermeter to record the value of current, electricity current, and then there's the magnetic field sensor to record the value of the magnetic field inside or outside of solenoid later on, and then connection cable to connect between the power supply, ampermeter, magnetic field sensor, solenoid, and rheostat. So for the materials, the first one is slinky solenoid and stand, which needs a minimum of length of 1.5 meters, and then a rheostat for the electricity. So for the basic theory, a solenoid is a coil wound that is made by wires which are wrapped in spiral shapes with certain length and sum of coils. When electric current is flowed through the solenoid, a magnetic field will appear, which is resultant of magnetic vector in each coil. So if we assume that the length of solenoid is bigger than its diameter, hence based on Ampere's law, the magnitude of magnetic field at the center can be calculated with the equation below, B equals mu0 times I times N over L. To calculate both of ends, right and left of the solenoid, we use the second equation, which uses 2L rather than L. So here B is a magnetic field, mu0 is the permeability constant, I is electricity current, N is number of coils, and L is the length of solenoid that is being used. So the first experiment is the relation of current towards magnetic field. In here, the data processing part, the length of solenoid is the same for this experiment, which is 1 meters. And then we vary the value of electricity current, which in this case is from 0.1 to 1 ampere, in which we get the value of magnetic field in millitesla, as it can be seen in the table. So according to the data from linear regression, we can get the graph as shown with the electricity current being the x-axis and the magnetic field being the y-axis. And the value of the equation will become y equals 0.1693x minus 0.0075. Please do mind that this is only an example for this module, and the data that will be given later on during the experiment will be different. So from the graph, we can calculate the mu0 or the permeability constant using gradient over n, or the number of coils, in which we get the mu0 value of 1.167 times 10 to the power of -6 Weber per ampere meter. So in this case, we use gradient over number of coils because the number of coils stays the same throughout the experiment. In this case, 145. So the value of permeability constant can be compared to the value from the reference, in which we get error percentage value of 7.08%. So the second experiment is the relationship between the number of coils and magnetic field. Here, the electric current will be the same, and we vary the x or the length of solenoid from 0.6 to 1.5 meters. In this case, we can get the N over L, or the number of coil over length of solenoid, which is coils per meter, and then we can get the value of magnetic field for each scenario. So from here on, we can get the pretty much the same as before. Using linear regression, we get the graph in which the x-axis is the n over L and the y-axis is the B. We can also get the value of the mu zero using gradient over I, in which the electric current is the same, 1 ampere, in which we get the mu zero value is 1.217 times 10 to the power of negative 6 Weber per ampere meter. So when compared to the value of vacuum permeability from the reference, we can also get the error value of 3.14%. Last experiment is distribution of magnetic field inside and outside the solenoid. In this experiment, we need to determine the magnetic field using the magnetic field sensor when the solenoid is with and without current. In this case, we do not measure the value of the magnetic field in the center of the solenoid only, but we also measure in the x equals 0, x equals 0.1 until x.1, and in the right and left end of the solenoid, which in this case we will get different values of magnetic field both without and with currents. So this is the report format. It is pretty much the same as previous reports. There's module and title, date, and time of the experiment alongside with your name, student ID number, class and session, and the assistant's name and student ID number, followed by lab condition, objectives, tools and materials, basic theory, data and processing, analysis to answer the analysis questions given before, and the conclusion. The conclusion must answer the objectives, and it must also be in the form of points. So that is it for this video. Thank you very much, and good luck for basic physics laboratory. Thank you.